Let's start with an image. Imagine watching a drop of ink spread in a glass of water. The ink doesn't jump from one spot to another in neat steps, it flows smoothly, constantly changing, influenced by the water around it. Now, compare that to how most computer models work. Data steps through a series of rigid layers, like walking upstairs. Today, I want to introduce you to a technology that lets AI models flow like ink, adapting to changes in the data's nature, evolving over continuous time. It's called Neural Ordinary Differential Equations, or Neural ODEs. So, what problem are Neural ODEs designed to solve? In traditional deep learning, neural networks work in discrete layers. Input goes into the first layer, produces an output, which feeds into the second, and so on. It's like passing a note along a line of people, each transforming the information in a fixed number of relay steps. But in many real-world systems, like tracking the temperature through the day, predicting a patient's vital signs, or modeling how populations grow, data changes are continuous and don't fit neatly into stages. When data is sampled irregularly, or the process is governed by physical laws, these step-based models can struggle. Neural ODEs flip the usual approach. Instead of stacking layers, they treat transformations as a process governed by a differential equation, meaning, they model how changes occur at every instant, not just at fixed points. Picture journeys instead of staircases. In a neural ODE, you specify how fast and in what direction the data is moving at every point along its journey. The network learns a function describing this dynamic, and then a mathematical solver computes the whole path from start to finish, just like predicting where the drop of ink will end up over time. Let me break down the core mechanics. In a regular neural network, each layer applies a function, changing its input, then sends it onward. Say you have 5 layers, your data gets 5 transformations. In a neural ODE, you define a function, parameterized by a neural network, that outputs the instantaneous rate of change for your data. Then, instead of passing through fixed layers, you hand this function to an ODE solver. This solver integrates, or adds up, the tiny changes over your desired interval, producing an output that essentially comes from an infinite number of microlayers, all smoothly blended together. This process is much like plotting a rocket's trajectory. Rather than jumping from point to point, you compute its continuous curve by understanding its speed and direction at each moment. In code, you set up the initial state, define your change function, and let the ODE solver do the rest, integrating to produce the outcome. Now, where does this matter? Here are 3 scenarios where neural ODEs shine. 1. Medical time series, irregular data from wearable devices or intensive care monitors, like heart rate sampled at variable intervals. Neural ODEs can adapt to each time gap, giving more accurate predictions and interpolations. 2. Physical system modeling, processes like chemical reactions, population growth, or mechanical motion anywhere the real world operates continuously, not in steps. Neural ODEs easily capture such natural dynamics. 3. Generative modeling, in AI-generated art or simulating realistic motions, neural ODEs allow models to generate smooth, lifelike variations between states, improving quality and realism. Why are neural ODEs important? First, they provide flexible modeling of dynamics handling data sampled at irregular times, or processes that change in complex, nonlinear ways. Second, they can use memory and computation more efficiently, as the solver can adapt step sizes, sometimes needing fewer computations. Third, they open up deep learning for domains where respecting physical laws, like conservation of energy, matters, by embedding those laws directly inside the neural function. Let me anticipate a couple of your questions. You might wonder, does this mean we no longer need regular neural networks? The answer is no. Neural ODEs are tools best suited for situations where your data or system truly evolves smoothly and continuously. For simple text or image tasks, traditional architectures remain practical and easier to train. Or, is this how models like ChatGPT or deepfake creators work? Not directly. While ChatGPT and similar language models use stacking of discrete transformer layers, the ideas behind neural ODEs have inspired new architectures and advanced research, especially in time-dependent and scientific data modeling. Over time, as we seek more efficient, adaptable AI, aspects of ODE-inspired training might augment or enhance current techniques. In closing, neural ordinary differential equations signal a shift from digital, layer-by-layer imitation of intelligence, to models that understand and predict the flowing, organic nature of change itself. As AI steps deeper into